Today's aircraft are an engineered mosaic. Every part is chosen for its job, environment, and cost. We combine stiffness, strength, toughness, fatigue life, corrosion resistance, manufacturability, and economics into one cohesive structure. That means designers think in systems. Where will loads flow? Which joints see where? What inspection access is needed? And how will material choices affect the whole life cycle? In short, material selection is not a single-axis decision. It's where physics, manufacturing, and finance meet to make an airplane that is safe, affordable, and efficient. Modern large civil airliners typically use a mix of composites, aluminum, titanium, and steel, each making up a meaningful share by weight and function. For example, the composite-heavy designs used on some recent widebodies are around half composites by structural weight, with aluminum, titanium, and steel covering the rest for skins, fittings, engines, and highly stressed parts. This mix delivers weight savings and corrosion benefits while keeping proven metals where durability, impact resistance, or cost favor them. Older generations leaned heavily on aluminum. In some classic designs, more than half the structure was aluminum, while newer designs move that balance toward composites and hybrid solutions. The shift isn't only materials, it's also manufacturing, automated fiber placement, resin infusion, and systems integration that allow larger, smoother parts and fewer fasteners. The result, newer airframes often weigh less and have improved fatigue and corrosion behavior, but they also require different inspection and supply chain approaches. Hybrid structures combine the best of both worlds: composites where directional stiffness and low weight matter, and metals where toughness, local bearing strength, or thermal tolerance are critical. Joints between the two types can be complex, so engineers design hybrid interfaces carefully, often using tailored adhesive joints, inserts, or transition laminates to transfer load while minimizing galvanic or thermal mismatch problems. Practically, hybrids let programs optimize performance without accepting the full cost or unknowns of an all-new single-material airframe. Mixed material airframes demand mixed inspection toolkits and maintenance thinking. Metals show visible deformation and corrosion, while composites can hide internal delamination and barely visible impact damage. That means fleets need both conventional visual and eddy current checks and advanced NDT like ultrasound or thermography, plus tailored repair shops and trained technicians. Operators must plan inspection intervals based on mission profile and environment, not just flight hours. The lifecycle cost picture changes when materials are mixed. Looking ahead, expect three broad trends. First, more hybridization and smarter joining techniques. Second, greater use of faster, tougher thermoplastic composites and recyclable materials. And third, localized additive manufacturing for complex fittings and repair parts. These trends aim to reduce cycle time, improve damage tolerance, and make aircraft more sustainable. But they also create new certification and supply chain challenges that programs must plan for early. That brings us to the end of Module 3. In this slide, you will find some of the references used in preparing the content and some additional links and references for further reading. The importance of material properties and how they are taken into account in various aspects of aircraft structures design and analysis are covered in our 4 modules of stress, fatigue, composite, and repairs. Please check them out if you are interested.